Alright, so let's now look at our example 3. So let's begin by reading our problem. A sample of 423 cell phone users shows 321 of them are iPhone users. At significance level 0.01 is the sample showing strong evidence that proportion of iPhone users is greater than 72%. And so now, in our first responsibility, let's identify the hypotheses. So we need to identify H sub 0 and H sub 1. Back into the wording of the problem. Is the sample showing strong evidence that proportion of iPhone users is greater than 72%? So this is the statement that we're trying to prove. And quickly translating this statement into mathematical statements, we're looking at P being greater than 72%. But then, as we're clear up to this point, we are a lot of time using decimals. And so 72% is formally 0.72. This is going to be our alternative hypothesis, which is H1 right here. So alternative hypothesis says P, the proportion of iPhone users, is greater than 0.72. And once we have found the alternative hypothesis H1, then H0 can be easily found by simply replacing, not the same statement again, but replacing the inequality with the equal sign. And that's how we successfully found our null hypothesis. And immediately looking at the alternative hypothesis, we can tell ahead that we will be using our test as the right tail test. We will be conducting our test as the right tail test. And so now getting into the problem. First step, once again, I am going to nail down the value of our sample that we're using. So back into the description of the problem, the reading of the problem. A sample of 423 cell phone users shows 321 of them are iPhone users. So this first piece of information right here is indicating for us that we're looking at our sample proportion. And we call that P hat is being given as 321 over 423. And calculation comes out to be in decimal, 4 decimal places, 0.7589. And of course, the sample size being used in this sample is 423 cell phone users. And once again, as soon as we realize that we are using a sample, provided that we are using our sample here as being at sample size 423 users in our sample, and that our sample proportion here is not the only sample that ever exists out there. And again, I need to remind, there are infinitely many other samples at the same sample size each. So in that way, the average, the mean value of our sample proportion, where symbolically I notate by a mu p hat, this mean or average of all sample proportion values must be equal to 0.72. And again, allow me to save the explanation of how and why I got this mu p hat to equal 0.72 at the end after we finish putting all the steps together to arrive at our final conclusion. But now after this step, finding our average of all sample proportion values, then we are going to find our sigma p hat, which stands for the average spreading or standard deviation of all sample proportion values. And this sigma p hat value can be found by the formula we learned previously in back in the days that we were learning about the central limit theorem. 0.72, that was our mu p hat value. We multiply with 1 minus 0.72, and we're dividing that by our sample size, 423. This quotient is to be put inside a square root. And again, in 4 decimal places, our sigma p hat value, which stands for average spread of all sample proportion values, comes out to be equal to 0.0218. And again, unless being specified otherwise, usually for sigma p hat, I would go for 4 decimal places in decimal. And so this is the average of all sample proportion values out there, including ours. And now again, once we realize that our sample proportion is not the only sample, it's only one sample proportion value among infinitely many others, then this sample proportion value that we are currently having relative to this mu p hat being the center of all sample proportion values, then our p hat, our sample, has a z-score. And again, I use this optional subscript p hat attached with our z-score to indicate this is a special z-score, the z-score of our particular sample that we're currently using. And here, the way to find z-score, again, our value, 0.7589, subtract the center, 0.72, and this center here is our currently found mu p hat, and divided that by sigma p hat value, so 0.0218 goes into the denominator. Calculation now comes out to be, and again, unless being specified otherwise, usually I would go with 2 decimal places for all z-score, for any z-score. So our calculation here shows the z-score here is a positive 1.78. And so let's take a quick pause right here to look at our checkpoint for consistency. So just like how I have done in the previous 2 examples, at this point right here, getting our z-score being a positive value, let's make sure that it's consistent with what we've had and what we have decided in the beginning. Our alternative hypothesis is saying that we want to generally prove that proportion of iPhone users, or anytime we're picking a sample, it should be generally above 0.72. And so our sample is consistent with that alternative hypothesis in a sense that it's having a positive z-score here, indicating that we are above this value being claimed. We are above the average, the center of all sample proportion values. The positive z-score is also consistent with the fact, even though I have not explained what exactly the right tail test is, but this z-score being positive is consistent with the fact that we are leading our test, we are running our test as a right tail test. And so now the next step is to calculate our p-value of our current sample. So our current sample here will have a p-value being calculated as the probability that among all sample proportion of size 423, we want to find the chance that our sample proportion being greater than or equal. So once again, being a right tail test, or seeing the right tail inequality to the inequality that points to the right hand side from our alternative hypothesis, then here I am going to be using the inequality that points to the right hand side. And I want p hat sub 423 to be greater than or equal to 0.7589, our sample value that we have obtained. So this setup right here, this formulation here, is the calculation step for our p-value. And so again, we can start imagining that on a bell curve, that represent all sample proportion values, capital P hat, for 23. If 0.7589 is somewhere, then this probability is equivalent to the shaded area to the right hand side. And so to find that area, or to find this probability amount here, it is the same as on the standard normal distribution. We're looking for a probability of having a z-score greater than or equal to, and this is where our z-score is becoming handy, 1.78. And once again, let's check for consistency again. But our shaded area here is a right tail area problem, and this is how it's consistent with our test being a right tail test. And now at this point, we are going to be using our LS&D program. And when LS&D program is looking for a z-score, we are going to provide 1.78 as our z-score. And so again, on my screen here, with my LS&D program being ready for work, 1.78 I enter for z-score and hit enter. Now the area left given from the LS&D program is being 0.962462 and a lot longer. But remind yourself, and as the picture is indicating, the area that we're looking for in this probability problem, or the p-value here, is the right tail p-value, is a right tail shaded area. So this is not the correct answer yet. So we need to subtract that answer coming out from our LS&D from 1. So subtract that answer from 1. So meaning 0.962, etc., and etc. must be subtracted from 1. And so now our final answer here in 4 decimal places can be 0.0375. So this is our p-value for this particular sample, for our sample value. But now, after this step, calculating our p-value, the p-value for our sample, then we must be deciding whether this p-value can tell if we have a strong evidence, if we can have our evidence, our sample being strong evidence or not. So the decision-making line is here. We need to compare our p-value. 0.0375 is to be compared with. So now look back in the problem, in the actual problem itself, the wording of the problem. Significance level in our problem is given to be 0.01. And so comparing 0.0375 with 0.01, this time our p-value is greater than the significance level. And so here, in this case, unlike the previous 2 examples we have done, here we have our p-value to be above, to be exceeding our significance level. So that means our evidence. So here's how we make our final conclusion. Our evidence is not strong evidence. Our sample is not strong evidence, cannot be used as strong evidence to, either you can say, to reject our H sub 0 statements, or to support our alternative hypothesis H1. So ultimately, as you have seen up to this point, anytime our p-value falls below significance level, that's where we said we have strong evidence. But in this case, since our p-value is greater than 0.01, then the final conclusion here is indicating that our sample is not strong evidence to reject H0 or to support H1. And again, back to the reading of the question. The actual question is asking ultimately as a yes or no question. Is the sample showing strong evidence that proportion of iPhone users is greater than 72%? But apparently in our work here, we have just now made our conclusion that our sample is not strong evidence. This sample here, based on this claim, is not strong evidence. And so now, ultimately, as an answer, we are saying no, it's not strong evidence. All right, so now we are looking at the explanations for the steps previously done in example 3. So we already came to concluding that our two hypotheses, the null hypothesis was P equals 0.72, and the alternative hypothesis was suggesting that generally P should be greater than 0.72. And here in this example 3, we were using a sample that was different from the sample we were using in example 1 and example 2. So our sample proportion value here, P hat, was equal to 321 out of 423. And this sample proportion in decimal of 4 decimal places equal 0.7589, as you already knew back in the steps written. And so, of course, the sample size here is being 423. So, again, all I need to re-emphasize is that once we can pick up a sample at this given sample size, then we must realize that this is not the only sample we have. There are infinitely many other sample proportions at the same sample size here existing out there. And so, in other words, this P hat that we have, the sample proportion value we have, is among the entire distribution, where I named that as a capital P hat for 23 this time. So any value of this random variable capital P hat for 23 is the proportion of iPhone users in a sample of 423 cell phone users. And so now this distribution here, this distribution of sample proportion values has a center, and symbolically I call that the mu P hat. Once again, recall for yourself the idea from the day we're learning sampling distribution of a proportion is that since we have infinitely many values to this random variable capital P hat for 23, and so this center here is the average of all possible sample proportion values existing out there. And the central limit theorem guarantees for us that this mu P hat would always equal P. And further, the central limit theorem stated that the average spreading, or formally speaking, standard deviation of all sample proportion values here, can be found by the known P multiplied with 1 minus P divided by the sample size n, and put that expression inside the square root. So these two results are guaranteed by the central limit theorem. So now, very similar to the argument that was made in example 1 and example 2, since we have here in our null hypothesis a claim saying that proportion of iPhone users is 0.72, then now I'm going to start out by saying, what if we let that be true? So what if we were accepting it? So if h sub 0 was true, then consequently, and allow me to start being brief now because we have seen this kind of reasoning quite sometimes already. But central limit theorem now guarantees, according to what we have learned, that mu p hat consequently must be the value being claimed in the null hypothesis, 0.72. Once again, quickly as a reasoning, because that's what we are currently accepted. We don't know if it's true or not, but if it was true, if it was accepted as the truthful value for population proportion of iPhone users, then the center of all p hat value would also be the same as that 0.72 value. And so further, consequently, we're going to have, according to the central limit theorem, sigma p hat will equal to the value claimed in the null hypothesis, 0.72 multiplied with 1 minus 0.72. And this time we have a new sample size being 423. I am going to put that expression, that quotient, inside the square root, just like how we've learned that from the central limit theorem. So calculation comes out to be 0.0218. And so now, as a reminder again, now if we accepted h sub 0 to be the truth, then the value claimed in the h sub 0 statement is now acting as the center of all sample proportion values. And this average spread right here, this sigma p hat value we just now calculated, is the average spreading, or average spread in short, of all sample proportion values being spreaded away from this center. And so then, again, after realizing that our sample is only one among infinitely many other samples, then from where our particular sample stands relative to this claimed value and now being at the center of all of the distribution of sample proportions, then our sample 0.7589 has a z-score, and we can calculate that z-score by doing 0.7589, the value of the sample proportion we used, minus 0.72 being the center, being the mean of all sample proportion values, and we're going to divide that difference by 0.0218, the standard deviation of all sample proportion values. And this, whichever comes out from this calculation, is being referred to as the z-score of our sample proportion. So it's just a calculation of a z-score, but here in this problem I optionally give a subscript p hat indicating that the z-score we have found here is the z-score specifically for the p hats that we're using, our sample proportion value that we're currently using. And so calculation came out to be a positive 1.78 for our sample proportion value. So our sample proportion value here has z-score positive 1.78. And now, on the other hand, the sample size currently used in our sample being 423, with this sample size, we can go ahead and multiply with our currently accepted population proportion value. And this product came out to be 304.56, which is a number well above 10. And also, the sample size we're currently using being multiplied with 1 minus 0.72. So I wrote the 0.72 in red ink here to simply indicate that currently this value is the value that we're only accepting as the truthful value for population proportion of iPhone users. And so with this sample size we're currently using, multiplied with 1 minus 0.72, we came up with calculation showed 118.44, which is again a number, a value well above 10. So similar to the arguments I've made in the earlier two examples, then the sample size we are using, these two lines here are indicating that the sample size we're using passed the requirements to allow our distribution of sample proportion values at size 423 to be on a bell curve. And this bell curve, this normal distribution, has center at 0.72, and with average spread, we found previously 0.0218. Or in other words, capital P hat 423 is a bell curve distribution. And so upon proving that our sample proportion values, the distribution of all sample proportion values being normally distributed at this center and that average spread, then when it came down to our step calculating the p-value of our sample, the calculation setup was the probability that among all sample proportion of size 423, we're looking for the sample proportion value being greater than or equal to 0.7589. And I will once again explain the reason why we're setting this up as a using the right hand side probability. But at least this calculation setup, now once we know that we're on a bell curve with this center and understanding that our sample value is being on this sampling distribution bell curve, then we can proceed with this p-value calculation as a bell curve area problem, where we're having, think about, here's our bell curve, 0.7589 is somewhere on this bell curve to the right of 0.72, and the area we're shading here is an area, the probability we're doing is an area shaded to the right hand side. And that's how we now can legally think of this area as the area on the standard normal distribution bell curve, where we're looking for z-score being greater than or equal to 1.78. And so now proceeding into calculating this area on the standard normal distribution curve, all we need to do is to find the answer from the LS&D program or any kind of technology to find the area shaded to the left of z-score 1.78 and subtract that answer from 1. And so according to the steps that we have seen earlier, our final p-value came down to 0.0375. And that's how we were able to compare this p-value with the significance level given in the problem being 0.01 to realize now that in this particular problem of example 3, we had our p-value being above the significance level. And now on the bell curve representing the distribution of all sample proportion values at size 423, then we already knew that this bell curve would have a center being 0.72, because we accepted, for now we have accepted that this was the truth, the true proportion of iPhone users. And again, any bell curve has a big fat area in the middle, where we refer to as the common area, where we would see values, even though being up and down from this claim value, but still being referred to as the values that are commonly fluctuated. On my computer screen, the wording of the problem in example 3 is indicating for us that with our significance level being 0.01, that means the areas, the two little areas outside of our common area, there's an unlikely area to the left, and this little tail being the unlikely area to the right of the common area. The significance level is now indicating that each of these little tail is a 0.01 area. So alpha equals 0.01 on each area, or we can think of that as a 1%. And so easily, again, the math can quickly tell us that the common area here is being as big as 98%. So that means those values being around the center, being around this claim value, being a little bit up and down from where this claim is, we can accept up to 98% of those values and regard to those values as the common values that we can commonly accept to be a little bit up and down from where the claim was. So in particular, the sample we have here being 0.7589 is clearly above the value claim in the center. However, we would like to know further whether this sample would indeed fall into the area to the right tail outside of the common area, where we call that the unlikely area. And again, I will be giving the explanation to why we are specifically interested in finding out whether our sample proportion value would fall into this unlikely area after I put all the details together. And so since we're particularly looking for whether our p hat is being in the unlikely area shaded as the right tail to the right hand side of the common area, this problem is again very similar to the very first example, example 1. We refer to this as the right tail test. And so usually, looking back at the hypothesis, the null hypothesis, indicating that we had a statement saying p equals 0.72, and our alternative hypothesis was stating that p is generally above 0.72. So usually, even though this is our actual explanation of what it means by being a right tail test, but usually by simply looking at the alternative hypothesis in the beginning of our testing hypothesis problem, that should be enough for us to be able to identify that our test would be either a right tail or a left tail test. So we were able to tell that our test in this problem would be a right tail test, simply by looking at the alternative hypothesis. And now our p-value calculated as the setup, finding the probability where we can find a sample proportion at size 423 being greater than or equal 0.7589. So again, graphically speaking, this calculation setup of our p-value is represented by an area shaded to the right hand side of our sample proportion value on this bell curve, 0.7589 as a sample value, as a value on this bell curve, where we have center being 0.72. And so calculation came out for this p-value to be, so our p-value calculated to be 0.0375. And the comparison with the significance level show that p-value 0.0375 is greater than the significance level given in the problem, 0.01. So this direct comparison here graphically means if this black shaded area represents our p-value 0.0375, then the significance level, the area outside of the common area, being less than, so I'm going to draw as a red area to the right hand side of our common area. But in this case, since the significance level is being less value than the p-value, then here we're going to be drawing the red area to the right hand side like that, being a smaller value compared to the black shaded area. So the black shaded area is all the way from here to here, whereas our red shaded area for the unlikely values is only here. So that means in that way, and notice how the black shaded area is exceeding the red shaded area, and so that means our sample, this picture right here, is now clearly showing that our sample is or must be among the common values. Because right from that point right here to another point right there, that's where our common area is inside here between the two red area, but the black shaded area, once again, as I have explained, is being larger. It's just a direct comparison, as everybody can tell. And so this black shaded area, since being greater than the significance level in red, and so our black area here must be exceeding that red area, so it pushed our sample value. So now I use that term, it must push our sample value to be somewhere inside of the common area, from here to here. And so in that way, that's how I can ultimately make my final conclusion, that p hat is or must be among the common values. And so, as a matter of fact, now p hat itself is, so being among the common values, it means now that p hat is a common value. All right. And so, with our p hat now is proven to be a common value, that leads to our final conclusion here, saying that p hat is not showing strong evidence, or p hat itself is not a strong evidence. Not strong evidence enough to reject h sub 0. That's one way of saying that, or we can conclude that our final conclusion can be stating that p hat is not strong evidence to support h1. And so why is it that p hat being a common value leads to p hat itself is not strong evidence to either reject h sub 0 or to support h1? So to answer that, again, think of the bell curve representing the distribution of all sample proportion values at size 423. With our null hypothesis stating that p equal 0.72, then we have already learned that this value 0.72 is going to be the center on this bell curve, of this bell curve. And this center is at 0.72. If we accepted that value 0.72 in our null hypothesis as a claim to be the truth, and so now again think about the person who made that claim. And so anyone making a claim is going to defend him or herself as, if any sample is showing a difference, then it is okay to be different because I am a human being, so I'm fluctuated, I'm maybe off a little bit. So from what we are saying, we're saying that, well, yes, if we find sample values that are fluctuated from your claim, but still within the common area, and we can also refer to these as the sample values that are commonly fluctuating away, then we're okay. Then we can accept your claim right here, or we're saying that there's nothing wrong with your claim, and according to our significance level given in a problem, then we already knew that there's a 0.01 area here, or another 0.01 area here, or we can think of these as 1% area here and 1% area there. And that's why I had this common area in the middle to be as large as 98%. That means if our sample proportion value being 0.7589 falls inside of this common area, then the person making this claim can defend that it's just one of those values that are commonly fluctuated away from this claim, because in the end, I'm a human being, so I claim something, but I can be a little bit off. And so that's what the meaning of this common area. If that was off, once we allowed up to 98% of those values around this area, indicating a little bit amount of being off here. If our sample is still inside of that common area, then that means it's still consistent with whatever being claimed. And so that's why in this case right here, since our sample really was inside of the common area, there's nothing wrong. Nothing wrong with the claim. Another way of thinking is that, as I have explained, then we are accepting up to 98% of values that can be commonly fluctuated away from this claim in the center. And so when we pick any of our sample, then our sample p hat is expected to be in the common area, because the common area is so big. And that expectation is at 98% chance. Okay, so we're expecting any sample, a lot of samples, because we are allowing some amount of fluctuating. And so that's why, and here in this case, we allowed up to 98% of values that can be allowed as, considered as values fluctuating away from this claim right here. And so any sample that we picked up is expected to be in the common area, and that expectation is at 98% chance. And so indeed, yes, our sample is in the common area. And so in this case, and further, our p hat is in the common area, just like we expected. So it just fell right into the expectation. And that's why that leads to saying that nothing inconsistent with the claim. And that's the reason why, since we failed to point out the inconsistency with the claim right there, that's why P hat is not strong evidence, or not showing strong evidence to reject H sub 0, or we can also say to supports H1, meaning there's not strong enough evidence to suggest that the proportion of iPhone users should be less than 0.72. We don't have enough evidence. We don't have strong enough evidence to support this. And so in this case, since P hat is not strong evidence to reject H sub 0, usually another way of interpreting this is that we failed. P hat failed to reject H sub 0. It's a different way of saying that. Or failed to support H1. And so at this point, after seeing 3 examples, it's good to make some generalization here. So first, anytime our p-value falls below the significance level alpha, then this leads to our final conclusion about our sample as being strong evidence. Our sample is strong evidence. And otherwise, anytime that our calculated p-value is greater than or even sometimes equal to the significance level alpha, then that means our sample is not strong evidence. And that's how we generally make our conclusion regarding our sample. And as a further general understanding regarding testing a hypothesis that can be drawn after we've done example 1, 2, and 3 is that being a left tail test or being a right tail test, now at this point of our learning, after seeing all 3 examples, then we generally regard to either one of these, either a left tail test or a right tail test, as a general one tail test, simply because in part of the process we were interested in finding out whether or not our sample value would fall either into the left tail, the unlikely left tail outside of the common area, or fall into the unlikely area to the right of the common area, or we refer to that as the right tail test. So only one of the 2 cases happened throughout our 3 examples, 1, 2, and 3. And so in that way of my explanation, then the significance level in any of our problem in example 1, 2, and 3 is being generally regarded as the one-tail or a one-tail significance level. And so being a one-tail significance level, it is the area outside of the common area. Okay, it's the area outside of the common area, but only on one side. And I have to open parentheses, either to the left or to the right tail. And so, as a graphical interpretation, with our significance level being notated as alpha, and now being a one-tail significance level, that means, graphically speaking, here's our common area on the bell curve. Any bell curve, then significance level is the amount, how big that little tail to the right-hand side outside of the common area, or here's another amount of being alpha, how big that area, that little tail area to the left being outside of our common area. So there's an alpha value here and there's an alpha value there, and that's what it means by being a one-tail significance level.